Hello everyone. So today I will share our work on real-time testing of satellite attitude control with a reaction wheel hardware in the loop platform. So here is the content of my talk. First, I will start with the motivation, then the hardware and software design that make this real-time test possible. Next, I will show how we set up the experiment, the several issues that we encounter, and how we deal with them. Then I will discuss the result, and finally conclude with key takeaway and future work. So let me start with some background. So reaction wheel array are a commonly used satellite actuator in satellite because they provide precise attitude control. Unfortunately, the wheel is degrade over time in space due to friction, heat cycle, or radiation. Therefore, there's a need for us to design a controller that allows the satellite to maintain its attitude tracking even if the wheel degraded or failed. So we designed an adaptive controller that actually address this issue. So this slide showed an overview of the controller itself. So the controller does two jobs at the same time. First, it be able to track the attitude, and it be able to estimate the reaction wheel health online. So in the blue box here is the adaptation law that we designed, and it is called integral concurrent learning. And in this scenario, the action wheel number 3 is degraded, but the controller doesn't know about it. So as a satellite maneuver in this adaptation law will help collect input and output data in real time, and will help ensure the conversion of the estimated health exponentially. So you can see in the plot here, after some time, the estimated health data convert to the true value, as you can see here. Up until now, we have validated the controller algorithm using the simulation only. As a next step, we would like to evaluate this controller in the hardware in the loop testbed, and the green box that you see here are what will be implemented in the hardware. So why do we need to do hardware in the loop testing? It's because it includes real-time hardware dynamics that is hard to replicate in pure simulation. We want to verify that the performance of controller will still good when there is sensor measurement noise or other hardware constraint. Therefore, in this work, we have two objectives. The first objective is to validate the controller. So to do that, we will connect 4 physical wheels to the controller, and we will induce some failure to the controller, to the action wheel, and we will have the controller run in real time on the Jetson Nano hardware. And objective number 2 is to have a proof of concept of the testbed. So we want to verify that the modular hill testbed that we are building in our lab work and can be used for other tests in the future. So now let's move on to the full testbed architecture that we have built. So it has 3 parts, 1, 2, and 3. So number 1 is called host computer or satellite simulator. And this simulates space environment, satellite dynamics, and sensor model. It used a ROS2 communication framework to send the estimated satellite state and desired state to the Jetson Nano. And number 2 in the center is the Jetson Nano with 2 ROS nodes running. So the first one is controller node that run the ICL controller that we talked about earlier. And then we have the reaction wheel node that convert the torque command to the wheel command to control the physical wheel. And number 3 on the right is the actual actuated hardware. In this case, it's actually the reaction wheel. And it contains 4 Maxon motor that is driven by a ePOS4 controller. And it also have encoder, Hall sensor, and current sensor to send the actuator state back to the Jetson Nano and also to the satellite simulator through the ROS2 network, therefore closing the loop. So the controller loop will be run at 10 Hz or 100 milliseconds. And for the sensor, it's sampling at 20 Hz. I also want to show what is actually being computed inside the controller itself at each time step. So the first one and obvious one is a controller that compute the following formula. And then there is the adaptation law that look like this and also contain some summation. What I want to emphasize here is that the summation here does not save all the past data. It only save the previous step plus the current step. Therefore, there's no buffer storage is needed in this controller. After we do that, we need to integrate this data dot with forward Euler to get data. And because data is actually equal to the reaction wheel health. And we need that reaction wheel health. We need to reaction wheel health because we want to compute the reaction wheel torque that actually depend on the reaction wheel health. Therefore, we need to compute a pseudo inverse in this case. Lastly, we also need to compute the finite excitation metric. And to do that, we need to compute this minimum eigenvalue of the summation of the 4 by 4 matrix. Therefore, we can see that overall the controller is very lightweight if you want to implement them in the hardware. So this slide here shows the actual test bed. On top, you see the satellite simulator that is run on Linux computer. And on the bottom is the reaction wheel setup that is set on the flat table. At the setup, we don't have air bearing yet. And I want to remind that please remember that this is related to one issue that we have. And as the next part, I also want to show the table that summarize the test configuration. And here the tick mean that it is active, will be used in the test, and cross mean that we will not use that. And because the study will focus on the heel part of it, I will just focus on this heel test ABC. And the idea is that we want to conduct the test gradually by replacing the model that we have in the satellite simulator and move that to the actual implementation in the hardware. So you can see here that for heel test A, the main goal is to test the uh, reaction wheel model with the real reaction wheel hardware. And once we have that working, we will remove that from the model and just implement that on the hardware. Same thing at the end, we will remove the controller and reaction wheel model from the satellite model by replacing them with the actual implementation on JSON Nano and connect with the physical wheel. So now I want to talk about in detail for each of the tests. So for example, in the heel test A, the main goal is we want to check that the reaction wheel hardware will produce the similar response as the simulated wheel model. So in this case, the wheel hardware have two mode of operation. There's a current mode and velocity mode. And during this test, we observe that the current mode does not work properly because there is this large dead band that happen in this type of operation, and it result in the large mismatch between the command and response from the wheel. Therefore, we decide to switch to the velocity mode that have a better response that closely match with the simulation. You can see that now it's closely matched with the simulation as you can see in the plot. Therefore, we decide to use a velocity mode for the rest of the heel test. So for heel test B, now we have the physical wheel implemented, and now we want to test the controller model with the physical wheel. And you can see that because of this test bed have we put the wheel sit on the flat table. Therefore, in order to implement this test, we also need to integrate the equation of motion to complete the setup. Therefore, we must provide wheel speed and wheel acceleration from the hardware. However, there's issue with this setup is that there's no direct way to get wheel acceleration. And to get that, there's two methods that we try. The first one is use the current sensor. Each of the method have its own issue. So with the current sensor, we have the issue with the dead band, similar issue that we saw earlier with heel test A. And the other way around is to use a numerical derivative of the wheel speed to get the wheel acceleration plus some filter. But it's also introduced an issue of a lag, so the phase shift delay that provides delay in the signal. Therefore, we cannot also implement this properly. So to make it work, we decide to implement the calculation block to compute a clean wheel speed and wheel acceleration to feed into the satellite dynamics. Therefore, disconnected this from the physical wheel. However, we still feed the velocity, the wheel speed to the controller because we want to test the performance of the controller when there's sensor noise. But with this setup, there is one limitation that we have is that we now cannot induce a physical wheel failure to this setup. Therefore, to emulate the wheel fault, we need to do that from the hardware, right, from the software perspective. And this issue is very unique to the setup. We don't think that we will present in the future when we upgrade the setup to the air bearing test bed. The other issue that also we also observe is that there's a small, it's a high sensor noise when the wheel speed is close to zero, called Hall sensor effect. And to mitigate this issue, we decide to add some initial spin at the start of the simulation, at the start of the testing. So now when we complete this test, now we can move on to actually implement the controller on the actual Jetson Nano. So to make this work, we need to reduce the gain of the KICL gain from 10 to 1, so one order of magnitude, because we observe that if you don't do that during the simulation, the ROS2 and simulation node will just stop running when the ICL term is activated. And we think the reason is that because the hardware cannot deliver the large torque that were okay in the simulation. This really show a mismatch between simulation and the actual hardware. So for the actual test scenario, we decide to run the simulation for 4,000 seconds, and then the guide then will switch between inertial and nadir to show the difference between. And for the reaction wheel Hell, we decide to set the Hell of the reaction wheel number 3 to be 50%. And the green value that you see over here is just a set some small change that we need to make to reflect the actual hardware spec that we introduce into the test, that different from the actual simulation. So now here the key result that I would like to talk about. So A and B show the tracking performance, and then for C and D it show the estimation performance. So you can see that with the reaction wheel in the loop, the controller still be able to track its altitude and be able to estimate the correct wheel health as designed, even though there is sensor noise or some hardware constraint that we introduced into the test. We observed that the conversion of the heel health estimation is lower than the simulation because we reduce the KCL to avoid KICL to avoid the torque saturation. So the learning is a little bit slower. So this can be improved by just more tuning. But overall, we can confirm that controller perform well in the heel test. Lastly, I would like to show some hardware performance metrics. So overall, we can see that the average execution time is less than 4 milliseconds, which is well below the budget of 100 milliseconds that we have for control loop. And other than that, we can see that the CPU and the RAM consumption are below 20%, which means that it will leave plenty of room for other implementation in the future for other tasks that we want to include in this future upgrade of the test bed. So to wrap up, I would like to summarize that in this study, we validate the ICL controller on Jetson Nano with real reaction wheel using the hardware in the loop test bed. And you can see that the controller perform well, even if there is sensor measurement noise and hardware limitation. This modular testbed work as designed, and we will reuse it in the future. And for the future work, I would like to update this hill testbed to include air bearing setup. And we would like to implement other things such as the attitude determination system into the Jetson Nano, and to be able to physically induce failure to the action wheel to make the test even more realistic. And that is all for my talk today. And if you have any question, feel free to reach me in this email. Thank you very much.